Hello friends, in this tutorial we are going to discuss about the properties of region of convergence of Laplace transform. Before we go into the properties, it is essential that we know about poles and zeros of any function. Usually, Laplace transform of any function x of s can be represented in the form of a rational fraction, and such type of representation is given by equation 1. Now, if you closely look at equation 1, then you will understand that at the points s equal to z1 or s equal to z2, etc., the value of xs becomes 0. That is why such points are called zeros of the function xs. So in other words, in general, at the zeros, the value of a function becomes 0. Similarly, if you look at s equal to p1 or s equal to p2, then at this point, the value of the function is infinite. These are called poles of the function. Therefore, in general, one can say that at the zeros, the value of any function becomes 0, and at the poles, the value of any function becomes infinite. Do not get confused. At zeros, the value of the function is 0, and at poles, the value of the function is infinite. Poles and zeros play a very important role in defining the region of convergence. In the following section, we are going to define some important properties of region of convergence, and with the help of a few examples, I am going to show you how those properties can be applied in order to plot the region of convergence of any function. First property says that region of convergence ROC must not contain any poles. In other words, if you plot the ROC correctly, then there will be no poles present in the ROC. Second property says that if the function xt is of finite duration, then the ROC will be the entire complex S-plane except s equal to 0 and s equal to infinity. Now there is something which I would like to elaborate. These exceptions, that s equal to 0 or s equal to infinity, they are not absolute. That means depending on problem to problem, these conditions can vary. That means for one problem, you can find the condition that it is entire S-plane except s equal to infinity. Maybe for some other problem, it is entire S-plane except s equal to 0. Third property. If the function xt is a causal function, then the ROC will be right side of the rightmost pole. Causal function means the function will be obeying cause and effect relationship. Fourth property. If the function xt represents a stable system, then the ROC, if it is plotted correctly, it will intersect the y-axis in the complex S-plane. Fifth property. If the function is a right-sided function, that means the function after originating propagates to the right side, then the ROC will be of the form real of s greater than sigma max, as it is shown in the following section. So real of S greater than sigma max, where sigma max is corresponding to the largest real part of any pole. Sixth property, if xt is a left-sided function, that means after originating the function propagates to the left side, in that case the nature of the ROC will be completely opposite. That means in that case ROC will be of the form real of S less than sigma minimum, where sigma minimum will be the smallest real part corresponding to any of the poles. Now in the following part of the lecture, I am going to show several numerical examples in order to illustrate the application of these properties of region of convergence. So once again I repeat the properties so that you understand it properly, that ROC should not contain any pole. If the function is of finite time duration, then ROC will be entire S-plane except some exceptions. If it is a causal function, then ROC will be right side of the rightmost pole. If it is a stable function, then ROC will intersect the y-axis. For right-sided function, it will be of the form real of S greater than sigma max, and for left-sided function, it will be of the form real of S less than sigma minimum. Now that we know the properties, let's take a few examples in order to understand the properties of region of convergence. Now for the first example, I am going to take a right-sided sequence, and for the second example, I am going to take a left-sided sequence. For example 1, let us consider xt equal to e to the power minus at ut. Now ut is the unit step function which is defined as ut equal to 1 when t greater than 0 and ut equal to 0 when t less than 0, as it is shown here. Clearly, because ut is a right-sided sequence, naturally e to the power minus at ut, it will also be a right-sided sequence. So the function xt will be right-sided. Now let us find out the Laplace transform of this function xt. From the table of standard Laplace transform pairs, the Laplace transform of this function can be written as x of s equal to 1 by s plus a. I repeat, we are not going to perform the integration methods, but in order to save time, I am going to refer to the standard table of Laplace transform pairs that are available, and it is 1 by s plus a. Now, since the function is a right-sided function and the pole is located at s equal to minus a, the ROC will be real of s greater than minus a. Okay, so it is of the form real of s greater than sigma max. Now look at the diagram that is associated over here, and in the diagram it will be clear that how this is being plotted. Look at the diagram. From minus a, the ROC is being plotted and it is in the right side. Let's take the next example. In this case, we take a left-sided sequence. xt equal to minus e to the power minus at u of minus t. Naturally here u of minus t, it is a left-sided function which makes the entire function xt left-sided. Again, without performing the integral, in order to save time, I am going to refer to the table of standard Laplace transform pairs. And from the table of standard Laplace transform pairs, x of s becomes 1 by s plus a, same as before. But because the function is left-sided, now the ROC is going to be real of s less than minus a. It is of the form real of s less than sigma minimum. And look at the associated diagram that is being presented here. If you look at the diagram, you can understand that it is on the left side of the pole. So in that way, we can apply the properties of ROC. So if you like this video, please subscribe to my channel and press the bell icon for more videos.